Okay, so I'm just going to start with a little bit of an introduction into texture mapping, just the idea behind it, what we're going to do. But after that, we're going to figure this out, how we do this in the program ourselves. But the idea to begin with is simply that we can imagine that we have a three-dimensional object here, and the only thing we've been able to do is basically say these vertices here have materials, and I either calculate lighting for each of these vertices, and then I gradient this color over the entire thing. Or I calculate normals and vectors here, I gradient those over, and for every pixel within this I calculate the color. But still I'm calculating that color from kind of the same material. I have some material for these vertices, I have some light that I'm setting up. So even though we can get some light effect on this, so we don't have the same color on every single pixel, we still kind of have the same material. So if we want to make detail in this, we're going to have to make that detail in our 3D model. So we're going to have to, do little bevels here and do all kinds of things with very, very small vertices to get this kind of imagined rough detail here if we want some kind of hewn rock or something like that. And then every single vertex here will have kind of a much smaller or much higher count of vertices. Each of them will have different vertices with different normals, which get a different lighting effect, so we can get this detail here. So we just have to make a more detailed model. But what we can do instead is to say, I want to map an image onto this. So this texture, so to speak, I don't actually have to model the texture with actual polygons and actual vertices. Instead, I can pre-render an image of the texture or the surface of this, and I simply want to take that image and I kind of want to draw it onto this. However, I want to do it in a way that I still get this 3D lighting over this entire thing. So I'm kind of getting two ideas in here at the same time. I want to pre-render the surface, but I also want, when I move this object around, for that surface to be affected by where the light is hitting it. So it's not completely pre-rendered or baked, as it is called. But instead, I have kind of a pre-rendered surface or pre-drawn surface texture, and then I add the lighting on top of it. And after we look at this, we can look at ways to use these textures actually for other things and lighting effects and get these kind of different types of maps. But for now, let's just imagine we have a color map, a diffuse color map, which is kind of the simplest use of a texture. So the idea is, for instance, I have just a two-dimensional bitmap image. And this is my image. And I want to take this image and I want to project it onto each side of this. So this side will look like this. This side here will look something like this. This side here will look something like this. So I'm projecting a two-dimensional image, which is simply a bitmap that I store in the memory of the graphics hardware. And I want to project that onto the surface of my three-dimensional image. This makes sense so far, this idea. Cool. And you've seen this in computer games, because computer games usually have low polygon models to be quicker to render them, but still you have this immense detail, like all these facial expressions and facial textures and beards and eyes and stuff like that. In very many cases, we have very low poly kind of, let's draw heads here. No, we have this low poly image of a face. It's just a few polygons here. Still, it might be some tens or even hundreds of polygons in this. But in order to get a properly kind of detailed image onto this, we take a JPEG or something that can either be a photo or a very realistically rendered face, which I'm not going to draw here. And then that is rendered on top of this, which means that this model here is in 3 dimensions. So as that turns around, light affects it differently. The environment affects it. But it affects it only in the detail that this model allows. And then we take a detailed image and we render it on top. So now the question is, in order for this to happen, what do we need in our program? So, and where would this happen? Where would kind of the main calculation of this happen? Like at which point am I adding this texture to the image? Am I adding it for every pixel, in the vertices, in many places combined? So if we draw a simple OpenGL pipeline here, mainly the vertex shader, and there's some stuff in between. Then we have rasterization here, and inside that we have our fragment shader. So we're kind of going to look at where different parts of this happen. So in the fragment shader, we're actually calculating the color for a particular pixel on our polygon. So that's where we actually kind of add this color from the texture. And that's simply the idea. Inside the fragment shader, we have some kind of sampler. We just need some data in here, in the sampler, which is actually the data from the original bitmap or JPEG or PNG image that has been put into a kind of in-memory bitmap image in our graphics memory. And this sampler here is a variable that allows us to ask this image for the color of a certain point in this image, where this image ranges from, or where the coordinate frame that this exists in is set up so that this ranges from 0 to 1 in this dimension, and from 0 to 1 in this dimension. So our image kind of lives in this two-dimensional coordinate frame where the edges are at 0 and 1 in this horizontal dimension, and from 0 to 1 in the vertical dimension. The horizontal dimension called u, the vertical dimension called v, which is the reason for u, v coordinates, which you've probably often heard UV map or UV coordinates, which is simply to say this is the mapping from the texture to the three-dimensional model. So if we leave the shaders alone for a while and look at this image, what we need here is to tell OpenGL somehow what basically set of coordinates here, some u dot comma v coordinates, should be sampled for this pixel. So in order for us to give OpenGL the information that it needs, like what do we have to set UV coordinates for? Can I have an answer? So we send vertices into the OpenGL pipeline, right? But here I'm looking for it for a single pixel. So I can't really send UV coordinates for pixels into OpenGL, the OpenGL pipeline, because that's what OpenGL does for us. We send in vertices, does a lot of stuff, and then it rasterizes it into pixels.
You have to send the bitmap as well as this alone.
Okay, I need to send this bitmap as information that I can sample from. But what do I need to send along the vertices?
Where in the picture you want each vertex to correspond to.
Exactly. So where on the picture I want each vertex to correspond to. If I draw this, would be something like this. I want this corner to correspond to this corner to that corner, this corner here to this corner here, this corner here to this corner. So that's the only information I send into OpenGL. I just tell OpenGL for each vertex that I send in, I have a UV coordinate. So the vertex now has the position, which is XYZ three-dimensional coordinates. It has the normal, which is an XYZ three-dimensional direction. And now it also has the UV coordinates, which is a two-dimensional coordinate telling OpenGL which point in this image it should correspond to. So what will the UV coordinates sent along with this vertex be?
0, 1.
Okay, 0, 1. For this vertex here,
1, 1.
1, 1. For this vertex here, 0, 0. So the UV coordinates here are 0, 0. For this here, we have the UV coordinates 1, 0. Okay, so these are really simple UV coordinates that just correspond to the corners of the image. So that's what we're going to start with actually when we kind of set this up ourselves. We're just going to see that we can get this to map to here. But if we go back to the shaders now, so the vertex shader, we already have an attribute here for the position, and we have an attribute for the normal. We're going to need an attribute for the UV coordinates, right? We're going to need to stick our UV coordinates onto the vertex itself, so that every single vertex that comes in, and our vertex is in these attribute variables that can be sent through these lists of vertices, position list, normal list, UV list. We need to get that in here. What is the main thing we need to do with these UV coordinates here? Like, what is the extent we can do to the UV coordinates in the vertex shader? Nothing, almost nothing. What do we need here? Let's imagine we're in the fragment shader now, and we actually want to sample this for this particular pixel. It's not enough for us to have the UV coordinates here, or here, or here, or here. No, we want basically some kind of, let's imagine it's just a triangle that's being sent through here. So we have this, this, and this. We kind of want some kind of weighted average, right? So where did we get that from? What variables do we have that allow us to get weighted averages of values from the vertices into a separate value for the pixel, which will be different for this pixel, this pixel, this pixel. Each pixel will have a different variable, or different value for these variables, but they will all be based on some kind of weighted combination, some kind of linear combination of these. Like, which variables in the shaders behave in this way? Varying variables. So if the only thing we do is say I'm going to make a varying variable, v underscore uv here, and I'm just going to set my uv coordinates into this varying variable, that means in the fragment shader I also have this varying variable for the uv coordinates, the same variable. So now I have access to a value for the UV coordinates, except I know when I'm running the fragment shader, I'm running it for a single pixel. And I know OpenGL will have made sure that I get a nice kind of averaged value from the other ones. And actually, we can go deeper into that later in order to take kind of certain perspective distortions and stuff out of it. It's not always a completely linear combination or a linear interpolation. But either way, it'll give us a value based on the vertex values that will be a good value for this particular pixel that we're in. Meaning that while we only sent in the number 0, 1, 1, 1, 1, 0, 0, 0, for all of these pixels we're actually going to get numbers somewhere in between. Numbers like, what is this, something like 0.25, 0.3. Well, this is something like 1/4 of the way here, and well, 0.6 that would be. And kind of 2/3 of the way up. So for this pixel, we should get, or for this pixel, sorry, we should get some number like that. A number like 1/4, 2/3, which are average from these 0, 1, 1, 1, 1, 0, 0, 0 values. But at this point, we should get something like yes, 0.25066. That'll give us a sample from this image, which will be from here, and that will be the color that you use when we draw this pixel. As soon as we go one to the side, we'll get some other value. We'll sample from another source here next to it, so on and so forth. This also means that the pixels in our texture image don't need to line up exactly to the pixels in this image. It doesn't matter if this is tiny on the screen, so we have a very small resolutions and the pixels are really big. What happens is we get a value for this and we sample from some pixel here and that value is used. Go to the side here, get another value. That might be, a lot of pixels in between here that aren't used from the image, but that's okay. The image will have enough resolution, or hopefully have enough resolution, that if this is tiny resolution, we'll just get a sample of that image that has lower resolution. If this gets to bigger resolution, we'll just utilize more of our texture image. And then we can think about things like storing several texture images depending on the resolution that we're using it for, so on and so forth, mid-mapping and things like that. But for now, let's not worry about that. We can even end up having higher resolution here than here. That'll simply mean that some of the pixels from this image will end up in more than one pixel in this image, and that's okay too. And that's just the resolution this image has, and we'll map that resolution onto what we have on the screen. So we're basically sampling from pixels here, pixels that we draw on the screen. Based on the UV coordinates in the corners, we sample from this image. You can see that this here is very different. So this image here, which is completely kind of horizontal and vertical here, will end up being projected onto something that has this perspective projection in it. But it'll happen properly because we're averaging between these values. So they go here up this line. We'll end up with pixels that are horizontal here. Questions at this point about something as simple as this, kind of one-to-one mapping, one image to one polygon, or to one quad here.
This feels very hand-wavy.
Okay, and not exact.
It's like you're skipping steps somewhere.
Okay. So let's look at the shaders again. So we've only kind of gone to where we're getting these values for the UV coordinates. So we're trusting the rasterization here. We've looked at that. It takes the values for the varying variables and it linearly interpolates them in kind of 2 dimensions over the entire polygon that we're drawing. So we're going to trust that. The question is what we do in here then. So in the main function, and also how we kind of get stuff to that sampler, but you're going to solve that as well. So first step, we need to get this image, which is just a bitmap or a JPEG or a PNG. We need to get that into our memory, and we need to somehow connect the data and that to this sampler variable in our shader. What that gives us is it gives us basically a connection to the actual image data, so that if I have coordinates, I can tell this image data I want the color from this image, or the pixel from this image, at the coordinates u, v. So does that seem concrete? So this is somewhere in memory. There are colors in all of these pixels, and this maps from 0 to 1. So if I say I have these coordinates here, 0.25066, it knows the resolution of its image. It might be an image that is 1024 by 1024. It might be an image that is 16 by 16. It doesn't matter. OpenGL, or the sampler variable here, will make sure that I send in something from 0 to 1, and it'll give me something from within this image in the correct location. So it'll basically normalize these values from 0 to 1 over the image. Different policies can give you different results if you go lower than 0 or higher than 1. You can have OpenGL say anything lower than 0 will just be interpreted as 0. Anything higher than 1 will be interpreted as 1. OpenGL can have a policy that wraps around and says if you give me something higher than 1, I will simply drop the integer part of it and leave the fraction and just use the fraction as if it's between 0 and 1. That means if I go kind of outside the image, it'll simply give me this pixel. So if I take this square here and say I'm going to set this to 0, 0, this to 0, 2, this to 2, 2, this to 2, 1. If I use the policy that just interprets everything higher than 1 as 1, I will get this image here, and then the rest will just be the color of the edge here, and it'll just be filled in like that. If I use wraparound, where it instead drops the integer part and just uses the fraction, I will get 4 of these images over a single polygon. And then I can go, in this dimension up to 3. It'll be like a little bit flattened versions of this. So on and so forth. So we're just sampling, we're just setting up a number, and we say this number we get by averaging the values for these vertices, and we take that number and we just say, give me the color from this image using that number. So that's the sampler, and we can sample from it that way. UV coordinates should be fairly concrete because we simply send the value per vertex, and then we use rasterization, which we have looked at how it works, how it does these linear interpolations to get these weighted averages for every pixel. So it'll take weighted averages of these, and it'll give us the correct value here, which means we kind of have a continuous flow from this value up to this value here, up to this value here, and a gradient between them over the entire surface of this. So it'll give us different values for UV coordinates, which will give us different locations to sample from the base image. What we need to do here is we simply need to find a way to read from the sampler. You can just find that online. It's just OpenGL shader language code. How we read from the sampler, we simply send into the sampler our UV coordinates, and we get information out of it. Then what's up to us is how we interpret that. So if we have a simple 24-bit color image, the simplest way to get textures working is to say, inside my fragment shader, I'm simply going to take this value that the sampler gives me. I say I have these UV coordinates here from the varying UV variable, which I've gotten from here. So I have this UV coordinate. I tell OpenGL, give me the color that you sample from this image that I have. I take that color and I simply use that as my diffuse color. And I continue with my lighting calculations here. Let's imagine we're in the static pipeline though, or we did our lighting calculations here. So we don't have anything to do the lighting calculations here. Instead we have a color from here. What the static pipeline did was it took the color that had already been calculated here in the pipeline, and it simply multiplied that color with the color that came from the texture sampler. So we can imagine if we just send in a white color and calculate lighting for a white color, we have the brightest possible value of that color based on the lighting. So it diminishes as it faces away from the light. So the lighting lies in what we get from here, and then we simply multiply what we get from the sampler with that. And that'll work exactly as if we just used the sampler as our color. If we're doing lighting calculations here, we can either say, well, I'm going to have a separate diffuse color, and I'm going to have the texture image. That means I can maybe do this texture image with a black image, here, smiley face, on a white background. And then I can use that same texture image to do different cubes with smiley faces on yellow backgrounds, and smiley faces on pink backgrounds, and smiley faces on different colored backgrounds by changing the diffuse color. What's more common today is to not have a diffuse color, do lighting calculations with that, and then multiply it with the texture color. but instead just take the texture color and use that as our diffuse color. And what's interesting, if we do the lighting calculations in the fragment shader, that means we have kind of so many more things that we can do with these samplers. We can say I can use this sampler as a diffuse image, then I can have another image that I use as a specularity texture, specularity map or specular map. And I can say I'm going to sample with these same UV coordinates, but from another image that simply has kind of grayscale values. And these grayscale values can represent something like raindrops, something like that. So you use this image of the smiley face for your diffuse color. You use the raindrop specularity image for your specularity. And the effect that you get when you move things around is that you have kind of a nice flat image of the smiley face, but it looks like it has these different specularities on it. Like some parts are wet and some parts are dry, so it has different specularity. Not over the entire polygon, but just you can have specularity here, not specularity the other places. Specularity here. So it looks like you have these wet spots all over the place. So we can do something like that. We can use the sampler as an alpha value for transparency. So we can have some parts transparent, some parts not. We can use it as a combination. We can have a 32-bit image and say we take all these 4 bytes and we use them as red, green, and blue and alpha, or red, green, blue, and specularity, or a combination of this. So super interesting things that we can do, and we simply do that in the fragment shader. We're already looking at something like I have a uniform value for specularity, or specularity color, a uniform value for a variable for diffuse color. In this case, I can instead read each of those from a map. The questions regarding this before I kind of bring this down, simplify it a little bit again, and we can start working. So to begin with, we're not going to worry about specularity maps and alpha maps and stuff like that. We're just going to say, I want to read in a color image in my code. So somewhere in our Python code, in this case, we're going to read in a color image, be it JPEG, bitmap, whatever. We're going to manage to get that into OpenGL. And we're going to manage to have a variable in the fragment shader that gives us access to that. And to somehow call OpenGL and say, this variable in our shader should have this image data behind it. This is something that we need to do in our code, so that when we run the fragment shader, this sampler actually has been connected to this image data. Just in the same way that any uniform variable has been connected to a certain number, we just send that number in there. We can connect this sampler variable to this image data. All right, so once we have that, we need to set up UV coordinates, and we need to basically sample from this sampler with the UV coordinates, and then see how we can use the color that we get out. So we get some color value here, some vec3 or vec4, depending on how the sampler works. We kind of have to experiment with this and see what works. So vec3, vec4 color that we get out of this sampler. So there's a function, I think, that we call sample something that takes in the sampler and the UV coordinates and we get out a color. Fine. And we need to use that somehow in our calculations. Take the color that we already have from our lighting calculations and multiply it with it. Fine. Use this color in our lighting calculations. Use this color as something else. Add it to the other one. Just see how we can make this image somehow affect our image. And to begin with, I want you to simply get whatever image you choose to project onto each of these sides of a simple cube. So start with a program that has a simple cube. It's showing the lighting works. Then you know that your fragment shader is working. Get this image to simply be drawn at least on one side of this, just to get that image. Then we can make it a little bit more interesting and say, can we take a texture that looks something like this? No, this would be a 5, yes. something like this. So we have this texture image that has this texture map for a 6-sided die on it. And can we somehow, let's imagine that this is just equal quarters. You can find different types of texture maps of this. It can be equal thirds instead or something like that. For the polygon, for the quad, for the side of the cube that I want this part of the 6-sided die texture to end up on, what UV coordinates do I need here? If this is equal quarters here, quarter, 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 half, 3/4.
1/4 half.
Okay, so quarter, half first down here. So 1/4, 1/2 up here.
1/4 3/4.
1/4 3/4. So do you get the idea of what we're doing here? Now I'm just mapping part of my texture image onto a whole polygon. And once we can do this, we can imagine how it's done more complicated, like the face that we drew earlier. We have this kind of semi-complicated model of a face that has some polygons. Then we have a single image with an actual detailed face with hair and all kinds of stuff. And we take this and we wrap it onto this. That means that this polygon here has to have UV coordinates that correspond with this part of this image. And this can get really detailed. And in the end, when we have these really detailed textures, we stop trying to think and actually write down the numbers like we're doing here. Instead, we need to have programs that actually do this for us and find the correct locations. So this point here, UV coordinates, just to finish this.
Half.
Half and half. And this point here.
1/2 and 3/4.
1/2 to here, 3/4 up. So we're understanding how this works. So I would like to see first that it works, that you get a texture image showing. That'll take a while. Once we have that, it shouldn't take too long to find a texture like this and wrap that around it. You have to experiment with things like, is the texture image starting from 0, 0 here? Is it starting from 0, 0 here? Things like that. You just have to experiment and figure that out. And it just depends on the system that you're working on. So we're not too worried about that, and you can figure that out as you go along, as you see the results. Are there questions regarding this? Do you find it concrete enough at this point to work with it, or do you still find it kind of like I'm just saying things and skipping things in between? Of course, I'm not writing the entire calculations of everything up here. But I think we have a fairly concrete image of what we need. We need to load an image into memory. We need a way to sample into that image using UV coordinates. We need UV coordinates for every vertex in our model. We need to set those up so that they are varying, so in the fragment shader we can use a weighted average. To sample that, get the color, use the color in our lighting calculations or as a multiplication factor. So is everyone ready to get cracking on making this happen on their computers? There's one correct answer to that question.
Yeah.
Yes. Then we'll get going on that now and stop this stream.